Hi, in this video, we'll look a bit closer at correlation. So we've looked at correlation before as a way to relate two separate distinct variables together. So I'll draw a line of correlation that might occur on this heights normalized versus weights normalized chart. And we might be able to extract that there seems to be a relationship between the two, and even go as far as to guess what a weight would be given a height with a fair amount of accuracy. So we might see here at about 2.25, we might expect a weight of about 2 normalized. And similarly, we could do the same with -2 and 2 for the normalized weight and height, respectively. And we also notice that we might have strong correlation sometimes, and we might have weaker correlation, like as we see on the negative correlation chart. But in this video, let's focus more on some of the properties of the correlation coefficient. So our first one is that it is symmetric. So the order of its arguments do not matter. So the correlation coefficient of x and y is the same as the correlation coefficient of y and x. Our second property is that the value of the correlation coefficient doesn't change if we translate the data. Scaling the data may change the correlation coefficient, but it will only change the sign and not the absolute value. More concretely, we can see that if the correlation coefficient of ax plus b, which is some scale of x and some translation of x, correlated with cy plus d, which is some scale of the dataset y and some translation of the dataset y, that's going to be equal to the correlation coefficient of x and y without any scaling or translating, multiplied by the sign of a and c, which are our two scale factors for the individual datasets. And we can go about proving that below. And then our final thing we're going to check out is our largest possible value is going to be 1 for our correlation coefficient, and the smallest is going to be -1. And when exactly those two cases happen. So let's go about proving some of these. So let's look at first our symmetric, but maybe we'd like to refresh on how we calculate the correlation coefficient in the first place. So we can see our formula here. The correlation coefficient of x and y is going to be equal to the sum of xi hat and yi hat over all I, all over n. So what this is saying is we're going to just standardize each of our coordinates and then correlate those two, or multiply those two together, add up what we get, and divide the whole thing by our size of our data set, n. Perfect. So let's see why it is symmetric. So we have the correlation coefficient of x comma y is going to be equal to the sum over all I of x sub I hat, y sub I hat, all over n, and since we know that multiplication is commutative, so x sub I hat times y sub I hat is the same as y sub I hat times x sub I hat, we can say that this is exactly equal to the following. Now, since we have this, we know that this actually matches exactly what our formula says. Sorry. So that is exactly that. So that's just the correlation coefficient of y comma x. All right. Fairly simple one-liner to prove that it's symmetric. How about let's prove translation? So if we are translating this data set, what are we doing? So we're taking some x. So let's set x equal the data set 4, 7, let's see, what'll be a good number? Maybe 13. It'll make for a bit of nice means. So if we translate the data set by 4, and that means just add 4 to each element, our new x is going to be, we'll just call that x prime, maybe. It's going to be 8, and then 11, and then 17. And let's see what happened to the mean. So the mean, we can remember it translates by the same amount. Let's prove that to ourselves. So 4 plus 7 is 11, plus 13, that's 24, divided by 3. That's going to give us a mean of 8. Similarly, 8 plus 11 is 19, plus 17 is 36. Divide that by 3, and we get a mean of 12. So we can see when we translate by 4, we also increase the mean by 4. So that's fairly handy. So let's look at what we actually do in our correlation coefficient calculation to see why this might not change. And we can remember when we translate, we don't affect the standard deviation at all. That was covered earlier in chapter 1. But we can look at how we calculate our x hat I, and we can see that it is x sub I minus the mean of x over the standard deviation of x. So let's go ahead and use that, copy that down here, and see how that works out for us. So we know that x sub I hat is going to be our x sub I, but we remember that our x prime is just 4 more, so it's really our x sub I plus some constant. In this case, it was 4, but we'll just call it c. And then minus the mean of x, but the mean of x was actually just the mean of x prime was actually just the mean of x plus 4. So same thing here. When we shift the mean, or when we translate our data set, we shift the mean by that amount. So we will have the mean of x plus c, and all of that over the standard deviation of x. So this is when we have a data set x plus c. So we're doing a translation of x and we're adding c to it. Perfect. So let's take a look at what happens. So we get x sub I hat equals x sub I plus c minus the mean of x minus c. So we can see the plus c and the minus c cancel out. And that's all of your standard deviation of x. And what we can notice is this is exactly what we had in the beginning before any translation. So now we can see that whether we translate x or we translate y, and that'll be a symmetric argument, we notice that the correlation coefficient won't change since our standardized coordinate won't change. So that goes about proving translation. Let's check out scaling and how that affects it. So what we can notice is when we scale a data set, we can use that property of standard deviation. So the standard deviation of kx is going to be equal to the absolute value of k times the standard deviation of x. And let's remind ourselves what happens to the mean as well. You can convince yourself of this by just plugging it in, but the mean also increases by k. So that's k times the mean of x. Perfect. And then, of course, every single element in x will increase by that amount. So let's also take a look at our standardization process, and let's see how this changes now. So we have our new x sub I hat, and this is going to be equal to, so all of our x sub i's, but our x sub I is scaled by a factor of k, so we'll include that there, and then minus the mean of kx, but that's going to be equal to just k times the mean of x, and then all of that over the standard deviation of kx. But that's going to just be equal to, as we said above, standard deviation of x and times the absolute value of k. So we're seeing a lot of k's on the numerator and k's on the denominator. Let's see if we can try pulling any of these out. So on the numerator, we can pull out a k, and on the denominator, we can pull out an absolute value of k. And then we have x sub I minus the mean of x all over standard deviation of x. Perfect. What we can notice is this was our original x sub I hat, all on the right. Let's see if I can highlight that in another color. So this all was our original x sub I hat that we would have expected without any scaling. And we can see all that's left over is actually just the x k over k, the absolute value of k. So let's take a look at what that does. When k is less than 0, we're going to have a negative in the numerator, negative k, negative value in the numerator, and divided by the positive version of that value in the denominator. So that is going to yield a -1 out in front. When we have k is greater than 0, then we have the same value in the numerator as the denominator. That's going to yield a 1. So here we can see that we either change our x sub I hat to a -1 or 1, depending on the parity of the scale. So whether our scale factor was positive or negative. So we can see that's kind of when we plug that in, that has the potential to affect our correlation coefficient, but only by changing the sign. And we can show that here as well. The correlation coefficient of x, y is equal to the sum over all I of, just scroll over here, x sub I hat, y sub I hat, and that's all going to be divided by n. Sorry about that. So here we see if we have the ability to change the sign of one of these, that could affect our correlation coefficient. So what will end up happening is we either get a negative times a negative, which will yield a positive, negative times a positive, which will yield a negative, positive times a negative, which will yield a negative, or positive times a positive, which will yield a positive. So what we can say is the sign of both the multiplication of each scale factor. So if we scaled x by a and we scaled y by c, the sign of a times c will capture our correlation coefficient difference. And we can see that's exactly how we got this part of our formula. Perfect.